Thank you guys again. Great panels this morning so far. And now we're going to be talking about quantum supremacy and AI. So I've got two amazing people here that come from two very different types of companies. But I want to start out just by kind of getting a level set of things. Ben, I'm going to open this to you. What's a quantum computer?
Yeah, we've heard a lot about quantum computers today, but we haven't gone back to the basics. And so Matt did warn me he was going to ask. Generally, I think Dimitri started giving a really great answer about this. Really, that there's a different kind of problem you can accomplish with a qubit that you cannot accomplish with a bit, and it really has to do with that information density in the system. So most quantum computers work by having a two-level system, a qubit, or you can have more if they call it a qubit, but most use qubits. And really you're talking about placing that qubit in a superposition between 0 and 1, and then creating correlations between those qubits. So using entanglement to kind of distribute information and distribute how information affects other qubits. And I would say that is generally what is special about quantum computing, is it's not just the superposition, it's really about those correlations and how when you measure certain qubits, it forces other qubits to collapse in certain ways, and that these correlations are really where this rich information density comes from. And of course, with that, you get to access different problems. So you build systems with these many two-level systems, many qubits. You make sure you can control them. You make sure you can read them out. And at the end of the day, just like a normal computer, what comes out is a bit string. It's a bunch of zeros and ones, but you've had all that control and you've been able to send gates to it and actually bring it through the calculation in a way where you are most likely than not reenacting some calculation on the physical level of those qubits. And so a lot of the first uses that people think about for quantum computing are really on qubits simulating the actual quantum world. And so people talk about quantum chemistry, they talk about materials, they talk about all these physically motivated scenarios where you'd use a quantum computer. And I would say one of the, of course, amazing things is it's not just that. And I think the great example of that people always point to, and I'll just point to as well, is Shor's algorithm. Something that doesn't seem very physically motivated, but can use that same information-dense landscape to actually calculate the prime factors of a complicated number.
So Lorenzo, is a quantum computer going to replace my computer?
First of all, I'll give you a very different answer, okay? So how many of you are one of these computers? How many of you actually know how this thing works? Do you care?
Yeah.
Yes. So I'm an engineer, okay? I just want to use the thing. So I think where you look at it is there are problems in computing that require a lot of computing power. Hours and hours, days. Okay, for those kind of problems, classical computing is a problem. Either it takes a long time or you consume lots of energy. So think of quantum computer as something that can solve those very complex problems that you find. Obviously, AI is the one that everybody knows about it. I come from an optimization world. So think about it, the supply chain plan, it takes 46 hours, and you cannot do it at the level of complexity that the real world is, so your answer is not that good. So I think of, from a utility perspective, think of quantum computing, something that can solve problems that for the last 30 years in my career, we couldn't solve. That's what's interesting to me. That's why I joined about a year and a half ago. And I think this is the biggest problem that quantum have, and we need people like you, because we're too caught up into the details. Like I came on and people started giving me this lecture and going, yes, I'm an engineer, but I can't communicate that. If I'm talking to a CEO, I want to ask him, what's your biggest problem that's compute intensive? And what does it mean if I solve that problem? And then you realize, well, I got this problem, I got that problem. Okay, what about if I can do that? You know, I have a quantum computer available today. Let me run it for a couple of months and I'll show you how much better the answer is. And then you buy. You can tell I'm the commercial guy in the room, or definitely in my company.
So again, in the vein of questions that come up a lot, then is quantum going to replace AI?
No, I don't think so. I mean, one of the amazing things that I think we're going to see from AI is the way people use compute resources is going to shift from engineers or people at different companies figuring out, how does this API call a CPU? How does it call a GPU? How does it call a QPU? To AI figuring out, I have a problem, I want to go solve it, and I can split that problem into calls to CPUs, calls to GPUs, calls to QPUs. So I don't think it's going to replace AI. I think it's going to be a tool that AI uses to do amazing things.
So, Lorenzo, there's often talk about different modalities of quantum. And I opened up this discussion by saying you guys are very different companies. What are the different modalities and what makes them different?
Yeah. So the primary one that you heard last night in the introduction is the one we all working on is this gate model. And the reason why everybody's so excited is because when it's ready, it will be able to address universal computing problems. The challenge with gate, which we all have, is there's a lot of science and engineering to get this thing to some useful level. So my company, 25 years old, they said, well, in addition to doing that, we better do something to get us there quicker. So another modality is called annealing. Annealing is not a generic computer, but it solves certain problems very well, like material simulation and like optimization. And that one is available today. It's been available actually for the last 3 years. The reason why I was brought on board is to say, okay, we've had this, but nobody knows about it, and nobody knows how to use it, and how do you get it out there? We have had customers, like a retail grocery chain in Canada, that has been in production for 3 years. So when I hear this thing of it's coming, yeah, it's true, gate is coming, and we have some debate how long it will be. But annealing is available right now, be available for a while, just nobody knows about it. And shame on me if I can't fix that problem in the next year. But and it is, you have to pick the right use cases. Complex problems in optimization, fantastic. Other things you can't. So that's why there are two different modalities. You have to be very careful. The nice thing, what we're trying to do is we're trying to elevate the whole industry to say, hey, you can solve some problems today and get ready for solving so much more once we have gate available, which hopefully we can get out in a few years. Some debate how long that will take.
So based on that, that really dovetails well with quantum supremacy, right? And this is a question to both of you. Google made a claim in 2019. How have things changed since then? But also, how do you both define quantum supremacy, Ben?
Well, I think they've improved upon that claim from 2019 with a same exact problem being done in 2024, but with twice as many qubits, and they've really shown that they can push that specific calculation to the limits of what one could imagine needing to beat a classical computer forever. So congratulations to them. The problem generally, though, is it's a problem that no one cares about. It is are quantum computers good at producing the outputs of quantum computers, which is a weird self-referential test. I think a lot of the time people want to talk about quantum advantage, where you do something first, and I think that's obviously important for companies, but I also think it's important for the industry, because if you can show quantum advantage, again, better, faster, cheaper, all of a sudden you're off to the races, and you can actually have this flywheel of innovation, even if that quantum advantage isn't it. So I'd love to hear
Yeah. So on an annealing related problem, which happens to be magnetic simulation, we did publish this year a paper that clearly demonstrated supremacy. So we benchmarked that at the fastest supercomputer frontier in North America here, and it would have taken that kind of problem close to 1 million years to solve that problem, a problem that we can do today in, we're talking about probably 25 minutes or so. And if you calculate the energy consumption to solve that problem on frontier, you're talking about the whole world energy consumption. And we can do it in the kind of kilowatts that was discussed before. So from our perspective, again, for certain problems, supremacy, from an annealing perspective, is here today.
So Ben, atom is very different in terms of neutral atoms. And how do you see them helping you guys achieve truly fault-tolerant systems?
Yeah, so when I started Atom, it was really with the goal of getting to a large enough number that you could actually build a utility scale on a computer. I think there's lots of platforms that have absolutely fantastic performance. I think, had people from IonQ here, you had people from Quantinuum. Ion traps best qubits possible, except for the fact that the number of qubits is really, really hard to scale on those platforms. And that's true of most every platform as well. Superconducting qubits, you go back into the fab. I used to work on superconducting qubits. You spend a lot of time, effort, and money trying to build better or bigger and bigger chiplets, or many, many chiplets that are, performing at their peak. The nice thing about neutral atoms is just that there's a lot of them. And this is something, I worked on as a grad student, where it was the exact same problem. Ion clocks, at NIST, were the best clock in the world. But the problem is you could only have a few trapped ions. Neutral atoms, once again, came to the rescue in that you can have whatever number of neutral atoms you want. And as long as you can build the classical infrastructure around them, you get, 98% of the benefit of trapped ions, but you just have all those qubits now. And that is why I started Atom Computing. That's why others have started other competing neutral atom companies, is that they are as close you can get to the scalable version of trapped ions.
So Lorenzo, what's the access that people have to quantum systems?
Yeah. First of all, let me clarify one thing to make sure it's clear. So you see gate and you get annealing. Within gate, there are different technology. You heard one. We are in the superconductive world. So Google, IBM, us are in that. Pros and cons, who knows? Hopefully everybody will succeed in doing that. Now, today, what's available, that's an interesting question from a go-to-market perspective. So before I came on board 3 years ago, folks that were here before, this is a supercomputer. So people want to buy a supercomputer, and they try to sell supercomputer. And yes, we do sell those. I have a small team that does that. And once in a while, we sell one of these systems, but, it's millions of dollars. So then we brought in, but people don't really want that. They just want to get the results. So we built a cloud environment, as we call Leap, that you just submit your problem through Leap, and then Leap is connected, running on AWS. Leap is connected fiber optic to our various production system. We're the only quantum vendor that has production systems. And then within seconds, you get a response back. Most people today access quantum as a service that way. Now, some people will want to buy one. The most recent one, actually, is the first hexascale supercomputer is getting built in Germany. And these folks are trying to crack the problem with AI and so on. And so they happen to have one of our systems. Actually, they bought that system to combine it with thousands of GPUs to figure out the problem that was described. How do you divide the workload on things that can be run better on an annealer? There are going to be aspects that are going to be better on a gate system. And then there are some things just building the GPU to divide the load up. So right now, I would say most people access QCAS, which is quantum computer as a service. And then we have about 5 different systems in the world.
So to both of you, what are some areas right now, and you touched on this, and we've kind of been talking in and out of AI, what are some areas right now that you see, or near-term use cases where quantum and AI can really work together?
The product we're out shipping now with Microsoft really is about how do you answer the problems of chemical engineers and material engineers that want to start using quantum computers, but also want to just get better at using classical computers. And so it's all around material simulation, catalysis, and things like that, where you actually already have a combination of small models you can run on a quantum computer. For us, it's logical qubits built top neutral atoms. But also, how do you integrate that with just classical simulations that are probably known by a few people in the world, or a kind of subset, but are not known by every chemical engineer or every material engineer or an engineer at some pharmaceutical company or something like that. And so we're kind of focused on making sure the questions they're getting asked or they're asking get answered, whether that's on a quantum computer or with classical simulation.
Yeah, on our side, a lot of it is we've worked with a number of customers that came with the domain expertise that we didn't have to apply that. So the first one, Japan Tobacco, as a division that does pharmaceutical. So they came to us last year and they said, listen, we use Gen AI to do a bunch of small molecule analysis and so on. And we think by combining an annealer, we can get much better results. So we went after, they brought a lot of expertise in RBM, which is restrictor Boltzmann machine. It happens to be a very specific machine learning technique. And we got some incredible results. Their goal is by beginning of next year, we should be actually in full production with that. And we actually released today with a press release on all those toolkits and so on that we built with them are now commercially available, so anybody can use them. We're also working with Triumph in Canada. They've done a bunch of work on diffusion models and so on and so forth, that again, for some other techniques. So the big work there is to get kind of experts in AI that understand all these techniques, look at the calculation workloads, and figure out which ones are suitable for an annealing environment. And right now we're driving a lot of partnership with people because we're showing no expert in AI to figure out, hey, come to us and let's put it through and figure out what the best use cases are.
And what are some of those use cases?
Well, I mean, the pharma kind of molecular development is definitely one of them. And then Triumph is a 3D generic technique that they're using for machine learning. So, it's always about kind of, model training and speeding that up, which is the biggest area of consumption in AI from a CPU perspective.
So, Ben, what are some of the technical challenges on scaling machine learning using quantum?
Well, okay, so I didn't quite get to answer that in some sense. So one of the things we're also thinking is how to take AI, take machine learning, and have it act like a filter. Talked about having to have AI that kind of figures out what you send to a GPU, what you send to a CPU, and what you send to a QPU. There's this other track that we've started to go down, which says if QPUs are a scarce resource, if it's incredibly, incredibly pricey to run a full model on a GPU, how do you have AI help that? And the way you have AI help that is you make AI be, honestly, the world's computer. So you have to train AI to how to be a quantum computer whose sole job it is to say, is there something very quantum in this configuration interaction between these molecules? Or is this just going to spit out something you'd have gotten with like mean field theory or something like that? And so there is a plan here about how you actually take quantum computers, take the outputs of quantum computers, and almost train AI to just give you this binary answer about when there's a really strong and interesting correlation that you need to go and check on a quantum computer versus when there is nothing and it's a classical problem or a nearly classical problem. Does that answer your question?
Yeah. So, and we'll get to some Q&A in a second, but I would say, what role, kind of going into that a little bit, or to switch it a little bit, what role does coherence time and error correction play in the race to supremacy?
Yeah, I mean, error correction is critical. There's just no question. I think that, we talked about different kinds of quantum computing, whether it's annealing or gate-based. And I think the critical difference between gate-based is, unless I'm wrong, right now we have a framework for what error correction looks like in gate-based quantum computing. We've published 2 papers now. Google published papers demonstrating various forms of error correction. Our competitors have published papers demonstrating various forms of error correction in gate-based systems. And we need to scale that. But that is why people are focused on gate-based, which is that there's a really clear framework for error correction. I think there's always going to be new codes coming out. There's always going to be more awesome codes coming out and things like that. But getting to a point where you can play literally 10 to the 10, 10 to the 11 gates is where you want your quantum to be. So more than 1 billion gates is going to be what your calculation is doing. Whereas right now people talk about mostly using physical qubits and going hundreds or thousands of gates deep. So there's a huge jump in orders of magnitude there. And the only way we know how to make that jump up is error correction. And I would say coherence time is critical in the sense of how you actually enact that error correction. But lots of different people and lots of different modalities have different coherence times. And I think there's positive and negatives. I like to tout my own because it's very high. But it's all based around who can get best error correction, because that is where gate-based quantum computing is going to shine in the end.
What causes some of these errors?
Well, see, that's interesting because that's the difference between gate and annealing. On the annealing side, you don't have the problem of error correction, and you can scale to, like our current production system is 5,000 qubits. So that's the advantage of annealing. But it's a very different idea. You're basically looking at a multidimensional energy field and asking the system, give me the lowest level. So it's you don't have all those issues, which is the reason why we can get there much quicker with that. But it cannot do things beyond optimization or simulation and so on. So that's why the two technology give you a different path.
And to kind of go out of this now, we've talked a lot about government. We've talked a lot about academia today. What role do some of those partnerships play for your guys' companies and sort of helping accelerate things?
Yeah. Well, on the annealing side, the biggest area for us to focus on is getting people that can use this power to solve real problems. So it's much more, we call it solution architects, but basically, how do you formulate in mathematical terms on a physician problem that can take advantage of the power of annealing? On the AI side, I think what, for example, we did with Germany, which was in the U.S., this was mentioned before. I think every supercomputer in North America should be coupled with a number of quantum computers to figure out how do you divide. It's always going to be, in my opinion, a hybrid environment where you got GPU, CPU, different kind of GPUs, and then you need a software layer that can figure out being much further ahead than the US in that.
So when Apple came out with the iPhone, it was like the calculator app and maybe like one other app on it, right? There wasn't a lot there. Is there anything that the quantum world can learn from that, or from a delivery of a system that nobody's ever had before access to? And are there elements today that software developers can start working on to have something available so that when that convergence happens, they're able to deploy?
Yeah, I mean, I think that's part of why we're selling systems. Is the idea behind selling a system is really about creating an ecosystem for applications companies and for industries within a country to go and access nascent quantum computing and build applications on top. Like, that is why Denmark wants to, or bought a system from us. They want to make sure that if there's 1, 2, 4, 10, whatever, successful quantum computing applications companies, that is within their borders. And they want to have, I don't even say control, but they want to make sure that they're both attracting folks into the Denmark ecosystem, or Nordic ecosystem, sorry, as well as making sure people in Denmark say, you know what I should do? I should start a quantum company in Denmark, in Copenhagen, because if I work with these folks, I might get wildly discounted or free access to the most powerful quantum computer in the world, or something like that. I think this is a kind of focus on getting people onto these systems and lowering the barrier to entry for them.
And what does that timeline look like in both of your opinions?
Well, I mean, from our perspective, one is obviously having systems is great, but what happens if you don't? So we invested in building this cloud environment so everybody can access to it. And we even have a program called Launchpad where anybody can submit an idea and we give them free access and free support to develop that. The other thing we have to put in is basically, if you want to build apps, you don't really, if you have to hire a quantum physicist to do that, there's not many of them going around. So we built this whole ocean, we call it, it's a open source SDK that anybody can download, build it into their application they're building. It's normal Python, to be physicists to use it, and embed that technology into it. At that point, though, the skill set there, again, is to figure out you go to mathematics, because fundamentally you got to represent the real world that you're trying to model into mathematics that the quantum computer can take full. If you take a formulation that runs classical and you run an our system, you're not going to get much speed up. You got to completely reformulate it. And so you need, I keep hiring in my PS group, master in mathematics, organic operational research, and so on. And finding them, it's, I have a 1 degree like that. There's not a lot of them, maybe a little more than quantum folks. But that's the world, just like, Wall Street started hiring all of these quant people who run mathematical modeling. Well, we need a lot more of those across industry to be able to take advantage of the power of these kind of systems.
Again, what's the timeline?
On our side is now. We have problems we're solving right now. We have production customers right now. So it's a question of connecting the dots and having people like, right now we're doing a proof of concept with a company that happens to do pharmaceutical pricing optimization. And today, a current system, they have 5,000 customers, and every customer takes them 6 hours to run. And somehow some CEO went to Davos and they heard quantum and told them, go look at a quantum thing. And the results are flabbergasted. We can do that 6-hour calculation in under a minute. And the answer we provide to them, because we can deal with many more constraints, is about 1 to 2% better than what they get from classical. And we're talking about a multi-billion-dollar operation. It's flabbergasting to them. And so they're now driving really fast to get to production. Interesting enough, to get to production, the limiting factor is not us, is they have to change the whole data pipeline, because all of a sudden we need this much data coming in quickly. And normally pipelines are not set up that way because it takes 6 hours. So the data is 6 hours old is fine. I mean, they want to get to the point that if I got a patient going into a pharmacist and they want to do a credit card transaction, can we do it in sub 5 seconds so that they can do the optimal pricing for that at that moment? That's where it's possible. Once they finish the data pipeline, we can get there.
Yeah, I mean, I would say that, for gate-based quantum computers, I think we're going to deliver, people are going to use a 50 logical qubit quantum computer next year. I think that by 2029, 2030, there will be utility scale quantum computers that displace HPC and can do things not 1 or 2% better, but things that are just impossible to do on classical computers.
So a few of the topics that we've talked about today are also about ethics, right? So what are some of the driving forces that you guys see around ethics in quantum?
I think that I said this to people actually last night. One of the things I've noticed is that, to me, the ethics in quantum are slightly easier than the ethics in AI. I think that quantum is a tool, and that most of the questions around ethics are all going to be about who gets access to this scarce resource and what is it used for. And I think the idea here is that the most important thing you could do is give a path to access these systems and solve gigantic challenges that could affect everyone in the world, like different kind of chemical modeling and catalysis modeling, different kind of materials research and things like that, and not just solely spend all of your quantum computing resources on portfolio optimization or something like that.
Well, for us, it was interesting because until last December, we had free access. Anybody could log in and you get access to the system. Then we had some Chinese in our system, and you see a bunch of papers. Oh, I cracked RSA. It was only 29 pages, so it's not a big deal. But holy shit. Suddenly we had to say, okay, we got to manage this. So now we put this launchpad in place where everyone is scrutinized, and I approve every single one of them goes through to make sure is the use case something that we actually want to support. So yeah, it's changed dramatically what we do operationally to give access.
So do you guys see a world in which you guys tampered down or have a gate, no pun intended, around like Shor's algorithm or something like that? Like, are you going to have use cases where you're like, hey, you just aren't allowed to do this?
We do that right now. I mean, if it's a use case around, security, and you're not in what we call LEAP approved country, we will not allow access.
I mean, certainly, I think there's going to see, like you said, I generally feel like export controls, like as we get closer and more demonstrations actually pushing into breaking RSA that's relevant for, whatever someone sent in the last 20 years, I imagine that there will be more and more export controls about what you can even access remotely in terms of quantum computing resources.
So we've joked about this where quantum has a communications problem. And some of the stuff that we've talked about is pretty dense, right? Why should the average public care about quantum?
I think there's just been such an amazing set of advances over the last, many decades that people don't realize how much is still to go and how advanced technology could get if we could solve the problems that we know a quantum computer could solve. And I think that's kind of why people should be excited, is that this is kind of, exponentially speeding up scientific innovation, and that most of everyone's everyday life is based off the scientific innovation that's been done over the last, 100 years. And I think that that's why people should be excited.
I mean, I was talking to Alan a few weeks ago about traffic optimization, and I certainly hate traffic. I don't know anyone in this room that doesn't, mind being in a car for hours, sitting in a parking lot, basically. But, I think that's another huge area. But what are some areas that you think, like, why should people care about quantum now?
It's the impact to their life. Like, we have these folks in Europe, first respondent, and it's about optimizing where they put fire trucks and, ambulances and police to be able to, shorten the time to respond. And, Oslo, there was at our qubits event, Oslo, the whole transportation system is now optimizing how many buses you have to make sure that the service levels are appropriate and so on. I think it's when you start talking about use cases that impact people, or for fun. I mean, we're working with a company that is the online betting world, and they're trying to experiment with, games where instead of betting the score of a game is who's going to get a soccer ball in the next 30 seconds. A problem that you can't do in classical, but we can quantum. And then as people get more comfortable, it's going to be like self. They don't really care what that goes into it. What do I do with it? So the more use cases are meaningful to the general public, I think the more natural is going to come. But it's just like I remember I was early days in internet in Silicon Valley, and for the first 3 or 4 years, the only use case you could think about it was parcel tracking. And I kept on saying, God, there's got to be more than parcel tracking you can do on internet. Well, now we don't worry about that. Everybody knows we can. So we're the classical new category formation where we need to find more useful use case that people care about. That's why, the magnetic one and supremacy, one reason I don't like about that, unless you are a, physicist, material physicist, you don't understand that use case. Because for use cases that people are a little more comfortable with. I want to go grocery shopping and I want to make sure there's enough people in the store to serve. Work for scheduling. Oh, okay, good.
So another one that comes to mind is blockchain, right? How is Bitcoin, for instance, going to be impacted by quantum?
Actually, don't know. Do you have to?
Yeah. So we just released, 3-4 months ago, the first quantum empowered blockchain. And that's all about, again, another heavy duty computing requirement. And quantum, you can do it much quicker. So we're actually working with somebody in that industry to actually take that technology that we proved out. We have a demonstration that we show at in Austin, Southwest by Southwest, to people that can actually do it right now, completely quantum powered. Now, these folks are running and say, let's do it so they can be a mix non-quantum, because we may not have access to a quantum computer. So you're going to start seeing solutions like that come into the market. The 6 areas that I focused on is AI is obviously one of them, optimization, blockchain, material simulation, or simulation in general, and then a bunch of engineering applications. Like we're working with an aircraft manufacturer that is trying to optimize the way fibers are rolled for a wing and make sure that we can see, or, when you look at the windshield of the plane, they just layer a bunch of chemicals there. What's the optimal way to derive certain characteristics? really difficult problems with classical.
So Ben, if you could have a magic wand right now and set one policy or investment priority today to secure U.S. leadership in quantum and AI, what would that be?
Well, I think the AI part is there's probably a lot you could do to change U.S. leadership in AI. So I'll just answer the component, which is that, all across the people are fine bumps and they are putting PCs. I say all across the world, but what I really mean is not in the United States. The United States has taken a very different approach. And I think that approach really comes from them saying, look, we have all the companies or many of the companies here. Why should we support them in this way? We already have the companies. We don't need to take them in force. We don't need to build the technology. Let's just wait next year and wait the year after. Let's wait the year after. I do not understand. At the same time, the same policymakers are thinking, okay, but we need to secure the quantum supply chain. Let's figure out how we shovel money to the supply chain. I think the right way to shovel money to the supply chain is buy a bunch of quantum computers. You hand me $10, I'm going to hand $9 of that or whatever to go and buy a bunch of components. And they'll be the components I actually want, not the components the U.S. government thinks I want. So I think the U.S. government should be actually purchasing quantum computers, knowing that right now, we're a small startup. We're not going to make profit off that. We're just going to turn around and spend that money on computing supply chain and workforce.
And Lorenzo, on your side, what are on that? What are some of the things that some of these leaders and policymakers can do to avoid being caught off guard?
Yeah, well, that I totally agree with that idea because, as opposed to thinking about, turning up a bunch of nuclear power station, why don't you take some of that money and actually bring quantum computer and focus on the application side, building applications that take advantage of that power. So that's critical one. The other one is I think there's an educational problem in general. I think if you look at the number of graduates, engineering graduates in China compared to here, is a joke. And mathematicians and so on and so forth. We need these computers are going to be very powerful, but if you don't have the people that can actually take advantage of it, and when I look at I scan user in our system. Of course, I don't know exactly where they are and so on, but you can kind of tell from last names and so on where they come from, and it's amazing the level of interest that there is in other countries, and it's not exactly a cool career, and I think it needs to be. Because we have a shortage, and not just for quantum. The fact that people are giving $100 million pays for people that know AI in Silicon Valley right now, it's a problem.
It's the shiny object.
What?
It's the shiny object right now. And we're seeing that across the investment space too, where not enough, to your point, not enough investment is going into quantum because the shiny object is AI. Yeah. So anyone who has an AI company right now is getting tons of funding, where in fact, I think that the two really work in tandem together. And I think that if you focus on both of them as a whole, you'd have a lot more optimal results. So with that said, I would love to open it up to questions to anyone here that might want to ask a few things. Anyone?
So I will say, I think, although I think it's proof of stake, I do think Ethereum has changed over to like a quantum safe cryptography thing. Do you think that they're, like I said, with Ethereum, I do know they just recently switched over to a different protocol specifically to make it quantum safe. Oh, no, they also did that like a year and a half ago. But I also think literally within the last week, they've switched over into a quantum safe protocol. I'm not as certain about Bitcoin. We'll actually give another example of a challenge like you just talked about, which is in the DoD. First off, there's a whole bunch of hardware that has encryption built in that is encrypted weightless. So D-Day or Q-Day or whatever comes sooner than people realize. And also, it's a much more situation because while you're right, Microsoft can go and Apple and whoever can go and flip and switch to quantum cryptography for all your browser sessions in like a moment. There's tons and tons of hardware throughout the DoD that is, it's hard. It is what it is, and it will have to either be entirely scrapped and replaced, or I don't know,
Can you talk a little bit on that a little bit more, because we actually had a conversation about this last night as well, which was data harvesting. So what is that, and why is that something that I need to worry about?
Well, I mean, there is the entire idea of store now, decrypt later, which is quantum computing is going pretty well. There's been lots of advances, and probably even before people in the last 2 years saw the advances, started thinking, well, why don't I just save everything I can see, and maybe I'll decrypt it later. And so, yeah, everything I would assume that if you are a sovereign state, I would assume every communique over the last 10 to 15 years is stored on a server somewhere in China, stored on a server somewhere in Russia, and that one day it's going to get read. Like I will build a quantum computer, others will build quantum computers, and our enemies will have access to that, and they will just read everything that ever got sent to the US government.
Yeah. I'd say one of the biggest issues or challenges that quantum has is hype, right? Because you don't want to be that company that comes out and says, I can do blank, and then not really be able to deliver on blank.
Sure.
And I think as a whole, it goes back to my statement before that quantum has a communications problem.
It definitely has.
And a lot of that really stems from the fact that we've learned from the past on people overhyping things. And I know personally, as I've looked at the space for almost 7 years now, the news cycles have been picking up more and more and more, to where now you have to really be discerning on what you're reading, because some of it could be perceived as hype, and some of it could be perceived as, wow, these guys really had an incredible accomplishment. So I think it's picking and choosing where you're getting your news and information from, but being careful. And I think that you guys are all doing a really great job at this across the board on making sure that the hype cycle isn't too up there.
I mean, I'm wildly biased, but I definitely think that money flowing to quantum computing, or private equity, equity flowing to quantum computing manufacturers is where people will make a lot of their money. Because I think that generally we can, at the end of the day, access a very, very large market. Like, that's why venture wants to invest in quantum computing, is a big payout. And as a quantum computing hardware manufacturer, I believe that especially if that resource is scarce, that is how you get a big payout. I think for vendors or supply chain, I think it's a lot harder. I think last few months aside, I think generally, we do not build an infinite number of machines, and I do not know if vendors are in the best place, considering that there is a scarcity, but there always are more than one vendor. Like, we can hop around from vendor to vendor, and I think that creates some challenges for them to fully capitalize on squeezing us, honestly. Quantum sensing, I think, is just such a very different industry, because I think here, quantum sensing industry, you really are trying to just make a sensor. No one cares that it's quantum. What you want is a sensor that is better than the one that's out there and cheaper. And that's wildly different than what I'm trying to create, or what we're trying to create. Is we're trying to create something very, very performant, and performance is the most important thing. It's not, is it 20% cheaper than a laser gyro or something like that. And so I think I don't know enough about the market there, but I think it's even harder to actually get to an end game.
But when you look at people like us, you got to think about it's hardware versus software as a timeline. It's like, I remember when NVIDIA was a joke. Well, now if you kept the equity for NVIDIA when I thought it was a joke to today, you would think about it a little differently. So, we are, and we at the core, we're a semiconductor company, and not that dissimilar, at least than NVIDIA is. So yeah, definitely you got to walk in with that time horizon. It's not the software time horizon. I've done a bunch of software startups. On the other hand, I would argue that, all that money that is going to AI today, there's going to be how many winners? I mean, obviously, this is typical Silicon Valley. I spent 20 years there. They're betting on one or two big winners, and the rest are going to fail. So you got to, I have so many friends that are into it. The latest, greatest is, agentic AI, and they're all building agentic AI. And guess what? 90% of them will fail. I think you're going to have, is definitely betting on quantum is a little bit of a longer term thing. Obviously, I joined a year and a half ago and we were trading at 79 cents and now we're probably 18 or so. So I'm sure investors in D-Wave on New York Stock Exchange have been very happy with that. But who knows? So being a public market, you can't control that much.
Last thing, I think that you touched on something really important to highlight. And I think for valuations of some of these hardware companies, it's almost hard to put a valuation to it, considering the fact that if somebody creates something mind-blowing, astronomical, whatever word you want to use, that solves a significant problem in our world on that system, how do you really put a valuation? I mean, again, we look at NVIDIA blowing up over the last couple of years because you had blockchain, or everyone doing Bitcoin mining and things like that, and then into AI. And, they're astronomically priced today. But when you look at some of these quantum companies, imagine solving, finding a cure for cancer on one of their machines. How do you put a price tag on what that machine would value at? So again, with that said, are there any other questions that anyone has? Thank you guys all so much.
Thank you.